What's up, people? This video is intended to help you with springs and work and energy together. Now, if you're AP, you've seen this before. If you're Physics 1, you have not yet seen this. So if we were to hang a mass from a spring, say, so there's a spring here hanging from some kind of ceiling, and we hang a mass on it, it'll stretch, and that is called X. That's how far the spring stretches. And the force that's being applied on this mass here is the force of gravity, but there's also the force of the spring holding it up. Now, if we were to continue to add more and more mass, I'm pretty sure you could figure out that the spring would stretch more, and what we get is a linear relationship. It's not giving too much away. Now from here, since it's linear, we can talk about slope, which is rise over run, or change in y over change in x. So it would be the force of the spring over x. Again, if you're AP, you have already seen this. That slope is known as the lowercase k. K is known as the spring constant. It's a constant for the spring. It's measured, as you can see from the equation here, it's measured in newtons per meter, force over distance. So literally, how many newtons does it take to stretch this spring a meter? The higher the spring's constant, the more force it's going to take to stretch the spring, and the stronger the spring. Simple as that. This, when you rearrange it, leads us to Hooke's law, which is that the force of the spring is equal to K times X. If you're Physics 1, there's a negative here. If you're AP Physics, they take the absolute value, which I can't stand, but it is what it is. So this is known as Hooke's law. Okay, now, slope is one thing we can do with a graph, but we can also do area. Fascinating, I know. So if we take the area, that is 1/2 base times height, which in this case would be 1/2 x times force of spring. But we have this expression here for the force of the spring. So that's going to be 1/2 x times kx, or 1/2 kx squared. Again, x is how much spring stretches or compresses from equilibrium. Spring stretches or compresses from equilibrium. Compresses from equilibrium, which is its natural resting place. I would like to add here, though, that this base times height, by the way, well, that's really, in written a different way, it's x times f, or force times distance, which equals work. And we know that work equals a change in energy. So that means that this is a form of energy, and it's known as U sub S, elastic potential energy, or spring potential energy. If you are Physics 1, we don't use U, we use potential energy of a spring equals 1/2 kx squared. Same equation. So Physics 1, we use the PE, AP Physics, we use the U. And that's it. So it's a new form of energy. You have that energy when an object is either stretched, a spring is either stretched or compressed, doesn't matter, either one, from equilibrium. That's it. So we just derived spring energy by taking the area of a graph. Let's do a sample problem really quick here. See how to do this. Now, this is the one that's in your handout, I believe. I'm not sure if it's AP or if it's Physics 1. It might be both. Okay, so here you have a scenario where there's a spring that's going to launch a mass up an incline. Initially, you can see from the problem that the spring is compressed a distance 0.2 meters, that's your x, and has a spring constant of 4,000 newtons per meter. It's going to launch this mass across a horizontal surface with friction, and then it's going to slide up a frictionless incline. I thought about making it with friction as well, but why do we need a double work problem? So I've drawn my picture. I've labeled initial and final velocities. Notice I've also, as per usual, once I'm on an incline, I like to side calc for that height. So here's the deal. Here's how you do springs. Nothing really changes. You do the same thing. You do the work energy theorem. So you have initial kinetic energy, initial potential energy, due to gravity. And again, if you're physics 1, you know that's PEG. But now we have a spring in the problem. No big deal. Just initial spring energy. Not a big deal. Plus any work done, final kinetic energy, final potential energy due to gravity. Again, if you're physics 1, that's PEG. And final spring energy, which, again, if you're in physics 1, that's PE spring. And that's it. So here are the questions. By now, you should be experts. Is it moving in the beginning? No. Is it above height 0? No. I'm assuming we're on the same page. We call this height 0. Initially, is the spring stretched / compressed? Either one. It doesn't matter. And the answer is yes. Initially, the spring is compressed. So I'm going to leave that there. Are there any forces doing work? Yeah, we got friction. Spring is not a force doing work. It's a form of energy. Is it moving in the end? Yes. We're trying to figure out how fast it is. Is it above height 0 in the end? Yes. And is the spring in the end still either stretched or compressed? And the answer is no. So I'm going to cross that off. Now, somebody else in the past had said, it seems like whenever the mass is touching the spring, that's when there's spring energy. So is the mass touching the spring in the beginning or the end? And it's in the beginning, so there's spring energy in the beginning. And I guess that makes sense, but it's really about stretching or compressing. And for us, I don't think we'll ever do a spring problem where something is, there's multiple springs and the spring is both either stretched or compressed in the beginning and the end. It's usually one or the other. After this, we just do a little math. That's it. Let's bring down some math. So bring down some mathy math. This is 1/2 kx squared. The work done by friction will be negative. At this point, you should know that already. So it's negative mu times the normal. Don't lose the distance. Afterwards, we've got it moving at the top. And we've got a final potential energy. Remember, do not, careful with this. Mass does not divide out. It's not in every term. But here we go. Let's sub in some numbers. We got 1/2. This is the part where you fast forward the video because this is the most boring thing in the world. 0.2 meters quantity squared minus mu. Normal on a horizontal surface when no other forces are applied is just mg. And I think the mass was 5 kilograms. So we'll do that. So 5 kilograms. Times 9.8. Again, speed this part up. This is boring. This is you watching me do a problem. Times 4 meters. Afterwards, that mass is moving, but we don't know how fast. Vf squared plus mgh, which is 5 kilograms times 9.8 running out of space meters per second squared times the height, which we calculated up there to be 0.927. By now, never just get an answer here because neither of us will be able to figure out what's going on that you got it wrong. So 2,000 times 0.2 squared gives us 80 joules of energy minus the work done by friction. Times 5 times 9.8 times 4, sorry about this, is 29.4 joules. Afterwards, we have 2.5 kilograms. Final velocity squared plus 49 times 0.927. 45.4 joules. So we're getting there. I got 5.2 joules equals 2.5 kilograms Vf squared. And I think from here we can take it and say that the final velocity, not square, just final velocity, divided by 2.5, and we'll square root that puppy, is 1.44 meters per second. All right. And that's how you put springs in a problem. Not a big deal. So I hope that was helpful. And just a couple, there's not too many takeaways, but let's take a quick look at some recaps here. So when it comes to springs, you're going to continue to use the work energy theorem, but include a spring / elastic potential energy. If there's a spring in the problem, include it. If there's not, don't include it in the work energy theorem. We haven't done springs up until this point. You never wrote it before. So don't write it all the time. Just write it if there's springs. Otherwise, what are you doing? You're wasting time. Spring potential energy is 1/2 kx squared, where x is how much it is stretched or compressed from equilibrium. K is the spring constant. And the question you ask is, initially, is that spring either stretched or compressed from its equilibrium? In the end, is it stretched or compressed from its equilibrium? That's usually like a mass being stopped by a spring. Usually it's a mass shoots a spring or a mass stops a spring. Those are your two options, basically. And the other way to think about it is when is the mass touching the spring? That's when you have the energy. And there's probably only one spring per scenario, so it's going to be either the beginning or the end, but I haven't seen a problem where we have spring energies in both. So that's about it. I hope this video was absolutely stunning. I would give it about maybe 3 out of 5 stars, and I would not change a single thing.